30 to 50% of your fractures produce 80% of your hydrocarbons.
That lends a lot of credibility. You know, if you come in and can be upfront and honest and say, you know, actually in this application, I think this product over here that I don't represent would be better for you. That all of a sudden now you become a trusted advisor rather than a salesman.
And, you know, I often say that we have all the requirements of space, right? Because it has to go underground and send us data from miles and miles away, and it has to work. Like, failure is not an option.
We'll put on, you know, a standard mule shoe. Ours is slightly different just for that, but it's, you know, everybody's got one.
The top drive and the drawworks really don't care whether the electrons coming at it are from a joystick or a PLC.
The panel, what you see here on the left, which is now controlled by one of my students, is showing you actually the control of our brakes.
As of now, geothermal is a pretty small market.
If you have tortuosity, the casing will be up against the side on part of the well. There won't be any cement there. The cement will have crescent around it.
So managed pressure drilling, it's been defined as a process to precisely control the pressure profile in the wellbore.
The key is being transparent with our clients in this case. So tell them what happened. If we had a failure, tell them exactly what happened. Whether it's our fault, whether it's whatever the issue was, we need to be transparent.
But I think it's very important for everyone in the industry to know what's out there and kind of what's happening downhole as well.
I've probably worked on over 40 different performance limiters in my career. If I miss any of those, and the computer is raising weight on bit, and I miss any of those, I have a train wreck. The computer's going in the ocean.
Here's your new colors, here's your new thing. We don't do that at all.
Here's the tattoo you need to get.
Yeah, here's the tattoo. Sorry about the last one. We used to fake that all the time.
Hello everyone, welcome to the locksmith door. I can't say it.
V-door locksmith.
V-door locksmith.
All right, everybody, welcome to the show. So happy everybody's here. This is the V-door locksmith show. I'm your host, David Gibson, where we are unlocking the secrets to success in the oil and gas industry. One interview, one technical presentation, and definitely one technical screw up at a time. I'm so happy it's Friday. Really excited. I had a great week this week. It was a short week. I think it was a holiday on Monday. I don't know. I worked the whole time, so I don't even notice these things anymore. All right. Yeah, guys, let me know where you're watching from. We'll give you guys a shout out here on the show. I forgot to put the little thing up, so it makes it look a little slightly more professional. Wow, I got a little put the white stuff all over me. There we go. Not looking half bad now. All right, guys. Like I said, let me know where you're watching from. Be happy to give you guys a shout out here on the screen. If you guys haven't already, do me a favor. Hit the follow button on LinkedIn, as well as they've got a new little feature. Haven't been putting this out there, but you can actually click on, I think it's just below the banner. There's a little button there that you can hit to be able to get notifications of when I put content out on LinkedIn. Main thing is for the LinkedIn live V-door locksmith show. You can also follow the hashtag on there. So 100 for the V-door locksmith intro. All right. Well, thanks, guys. All right. We've got Mr. Travis Bowden tuning in from Western Oklahoma. Thank you for being here, sir. John DeWart is in second place today because obviously Travis got in there before him. Usually the first guy to be able to comment. John, thank you so much for all your support. It really does mean a lot to me and to all of the guests that come on here as well. I know it's great to be able to have people watching. Abdullah tuning in from Cairo. Thank you for being here, sir. Johnny, I know he's on the other side of the pond. I just don't know exactly where. I think the Netherlands is where he's usually tuning in from. And he's tuning in from Saudi Arabia. Thank you for being here. All right. Ian tuning in from Magnolia. Our infamous LinkedIn user from India. All right. Mohamed says 100 for the V-door locksmith intro. Thanks, sir. And he's tuning in from Irving, Texas. Frank from Anchorage, Alaska. And this morning, Pete Stetson. Pete, aren't you supposed to be in a meeting or something? Oh, my gosh. Guy next door is always in meetings. But, Pete, thank you so much for tuning in. He's part of the Deep team. His coworker, Cade, was on the show not last week, a couple of weeks ago. All right. Good group of guys there. All right. William Abercrombie tuning in from San Antonio. Oh, Andrea, thank you so much for tuning in. I don't know how many of you know this, but formerly we used to have Minute with Andrea. And prior to that, it was Minute with Keith. Prior to that, it was Minute with Fahim. Andrea used to be on the show almost every Friday. Absolutely amazing person. Great drilling engineer. Glad to know she's tuning in. All right. Also, Luis Hernandez. King, who just got his drill bit sent in the mail. Speaking of which, y'all can start doing it now. This is one of the messed up 3D prints. I don't have a good one that's here. I think I've given them all away. All I've got in the office right now are these screwed up ones. And I think I'm up to 20 of these in the office now. So y'all can start putting in #Corva if you want as we go through this. But I'm giving away one of these. King he's already won 2 of these. And he's continued watching the show. He's going to have a whole host of these here pretty soon. We'll have to keep making new ones. Isabel tuning in from Egypt, and then Mr. Robin McMillan saying hi from the Energy Corridor. Robin was on the show last week. I've got amazing stuff to be able to put up about this, so this is perfect timing. Great segue into this little piece of content.
Go Robin McMillan.
I approve of this message.
All right, so Robin McMillan is running, or he has been nominated to be technical drilling director for the board of SPE. And then there were some people who challenged it, not so much challenged him, but just kind of challenged the process of who gets to be put on the board. And so now there's actually going to be election. So it's very important if you are an SPE member to be able to vote. I have put in my vote. As you can see here, I voted for Robin McMillan, Robert Hamad, as they were all 3 of the board nominees. And Robin is an absolute amazing person. He has done a lot of volunteer work within the SPE, IEDC, and Alphabet Soup community that is here in the direction, or not just directional, but in the oil and gas industry. So definitely a worthy cause there. If you haven't done it already, please put in your vote. All right. Oops, wrong buttons. Got to go back over here. Yeah, there we go. Frank's got the right idea. Start doing it. Oh, wait, hold on. Yep, we've already got that entry locked in. Start doing it now. Put in your #Corva. Banners, no brand. See, this is what happens when I have to run the show and I don't have Tracy behind me doing everything. All right, put in #Corva. We've got an absolutely amazing partner that has been working with us here on the show to be able to continue bringing you guys the show and to be able to talk about amazing things in data. All you need to do is type in #Corva and you guys will win one of these drill bits. Not one of these DVR bits that I've printed out, but actually a nice one, right? It'll have the rest of the bit here on top, just like Frank did. It'll have the rest of it. It'll look cool on your desk. It says Gibson Reports on both sides, both upside and right side, like that. So type in #Corva and check out this quick message from them. This is your Corva Insight of the Week.
A typical oil rig generates up to 2 terabytes of data every day. With that in mind, one of the biggest challenges in the industry is how to extract knowledge from vast amounts of data in a fast and reliable way. Machine learning is a subfield of artificial intelligence which focuses on simulating human learning behavior using the data and algorithms. The main goal is to let computers learn on their own, without assistance from humans. Machine learning algorithms are divided into 3 main categories, including supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, the algorithm learns from the offset wells data to capture hidden patterns. In unsupervised learning, there is no ground truth to match, and the algorithm independently groups the data based on their similarity. Reinforcement learning is the most complex of these 3 categories. Reinforcement learning directly mimics how the people learn from their interaction with the environment by receiving positive and negative rewards. Machine learning algorithms are the future of the industry, and the future is now.
All right, awesome. Thank you so much to Corva for being able to provide that. That was your Corva Insight of the Week. All right, let's get this up onto the screen. Here we go. That's not big enough. There we go. All right. We've got 11 entries so far, and I've seen a couple of people that have entered this. Man, it's getting better and better every week for people to be able to win this thing. So, all right, here we go. And anybody else going to put in #Corva? I mean, literally, it's not that hard, but, you know, we've got over 40 people watching, 11 people know how to use their keyboard. All right, and the winner this week is Ismail. Ismail, send me a DM on LinkedIn, and we will get you a drill bit sent off to you. Not this one, but one that's nicer. We'll get that sent off to you, and potentially some Corva swag too. If any of the people from Corva are watching, they said that they were going to send me some swag. So, all right. So now it's time to get on with the show. We've got an absolute amazing show for you guys this week. This is something that I happened to come across on LinkedIn. Sounded like some really, really cool technology. And not even just technology, just the thought process of being able to do this stuff. So I'm going to welcome in the first person and then let him introduce his entire team. All right. So this is Mohamed Khaled, or Dr. Mohamed Khaled. Doctor, thank you for being here on the show, sir. You let me know who you want me to bring on next, and then we'll get them here on the show.
Yeah, sure. So thanks for having me today. It is a great pleasure to be with you guys. So my name is Mohamed Khaled, and today I'm a postdoctoral researcher at the University of Texas at Austin currently. Before that, I got my bachelor and master's degree in in petroleum engineering from Suez and Cairo University in Egypt. And last year, I got my PhD in petroleum engineering from Texas A&M University. And basically, I worked with Halliburton before my PhD for around 5.5 years as a directional drilling field engineer and a drilling solution engineer. So yeah, that's all about me. And I'm really happy to be with you today. And yeah, you definitely, you can start with Dr. Gilden, so, because he was our supervisor of the project.
Hello, everyone. Thanks for watching the show. So I'm Eduardo Gilden, professor here at Texas A&M. It's a pleasure to be here, and I hope that you like what we developed. Thank you.
All right, who do you want to bring on next?
Dr. Moha.
All right. Hello, everyone. I'm Moha, also from Texas A&M University, Department of Aerospace Engineering. Really glad to be here on this show. And I'm a postdoc researcher at Texas A&M. Yeah, thank you.
Enrique.
All right. Next, Dr. Enrique Lozoya.
Awesome. Hey, everyone. Hello, this is Enrique. I'm a postdoctoral researcher at A&M, working on the Dr. Lerner and on geothermal wells. So I'm happy to be here and hope you like what we developed.
All right. And the last member of the... Oh, sorry. Keep going.
Yeah, no, go ahead. That's it. That's it from me.
I'm just... you guys are the smart ones here, not me. All right. And the last member of the team?
Yeah, Mr. Costin.
Howdy, everybody. Yes, so last but not least, my name is Al-Qasim Ibrahim Tuli. I'm a Master of Science student here at Texas A&M University. And thank you, everybody, from tuning in from all over the world. Thank you.
Yes, definitely an international audience. All right. So, Mohamed, so we'll go ahead and let you start with the presentation. Everybody, if you guys have got any questions, please feel free to shoot them off. I know that I'm going to have a ton of questions regarding this topic. So if you want to get yours in, you need to ask them now, right? Because I might just take over all of the questions. All right, guys. So I'm going to go ahead and take everybody back off real quick. Thank you guys for all being here. So what we're going to do is Dr. Mohamed's going to give his presentation. And then as we go through the presentation, y'all start to rack up all of y'all's questions. And then we'll bring everybody back on to be able to do the full-blown Q&A. All right, so here we go. Add the stream. There we go. And I'm also going to.
Okay, awesome. So hello, everyone. So today, basically, presenting on the behalf of Texas A&M Drilling Automation Team. Like the main idea we are trying to present today is how we can use that Tensegrity concept in building lightweight drilling rig to improve the drilling performance. So our agenda for today, I'm going basically to start with give you a brief introduction about the background and the motivation behind the project. Then briefly, we are going to discuss about the mathematical models and the different simulation analysis we conducted before building the physical drilling rig. After that, I'm going to show you the prototype drilling rigs that we built at Texas A&M University and the capabilities that the drilling rig currently had. And finally, I'm going to end up by summary and conclusion. Before I would like to start, I would like to introduce the drilling automation team. So basically, drilling automation team members is around 14 members from undergraduate and the graduate level. And the most interesting thing about this team was it is very diverse. So we are speaking about students who are from 6 engineering departments, different degree levels, starting from freshman till PhD. So it was really interesting to see how all these minds come together to build a lightweight drilling rig. The project was basically supervised by 4 faculty members. Direct supervision was from Dr. Gilden, who is a professor in petroleum engineering at Texas A&M University. So as David introduces us, so my colleagues and I, after the presentation, will be happy to answer your question. And I guess it will also be interesting to hear from them their insight and experience about the project. So starting first with the background of the project. So the story started when NASA announced the Rascal Special Edition competition, Moon to Mars, Ice and Prospective Challenge. And the main mainly this competition was to support NASA's approach for human future space exploration. So the competition was simply allowing engineering students to design and build a prototype drilling rigs that can drill and extract water from subsurface formation, and also assess formation in a simulated lunar and Martian formation ice. And when our team at Texas A&M University heard about the competition, we were really excited, because since some of our team members are from petroleum engineering background, and as the audience knows, oil and gas industry has a large experience in drilling thousands of feet in subsurface formation. However, the biggest challenge we faced was that one of the objectives of the competition was to design a lightweight drilling rig. Because, of course, sending a drilling rig to space or any cargo to space is not a cheap process. So you need to design a lightweight drilling rig. And basically, when we try to implement in the first stage and use, the conventional drilling shape that the oil and gas industry using, which is basically what we call lattice structure, we find that the structure will be heavy. So a small introduction, what we can see here is the drilling rigs. It's basically a rotary type drilling rigs. And how we drill the formation, we transmit rotation and weight to the drill bed so that the bed can drill rocks inside the formation, right? Of course, there is different systems in the drilling rigs, starting from the hoisting system, circulation systems, well control system, etc. And as a matter of fact, a lot of researches have been conducted, in improving these systems. But what is really interesting to know that the direct structure that you can see here in this picture that we use nowadays is very similar to the same structure was used back in 1858 for the first well drilled in Pennsylvania. And if you spoke with anyone of the drilling folks and asking them about the drilling move, they are going to say it is an hassle. Because if you are going to move the drilling rig from a location to another, you need to dismantle this structure into big bases, and it takes a lot of time to move from one location to another, which consume a lot of money. And when we reached this roadblock, we started to think out of the box and try to look around from what other industry is using. And basically, what grabs our attention that we find that the aerospace disciplines is basically using tensegrity concept to build lightweight drilling rigs. So tensegrity is basically a coined word of attention and integrity. And tensegrity, it is just a structure where it composed of a network of compressive members that we call bars. You can see here in gray, and a tensile member, which called strings, that you can see in a red color. And the biggest evidence about the reliability and robustness about the Tensegrity concept we can observe from biology. If you check the structure of the DNA, the fishtails, animal spines, etc., all of them structures are agree with the Tensegrity concept. Even in other engineering departments, like designing a massive building like bridges, we use Tensegrity structure. Robots nowadays also are using Tensegrity structure. And the main reason about the robustness and reliability of Tensegrity, it is a mass efficient. So basically, you are going only to use the material you need to withstand different loads. Also, it has a kind of a shape control. So I'm going to show in a minute how you, by changing, the tension and length in the string, you can even change the rigidity of your structures. And as we can see in the picture, we are speaking about a one-dimensional members. So simulation is more easier and more accurate. And this is why Tensegrity structure was a good fit for our application. Of course, after we select or decided to use Tensegrity concept, we started to build our numerical models. And basically, we conducted multiple simulation. And the main reason was to optimize the Tensegrity network by selecting what is the type of bars, what is the length of the string, the tension, even the shape of the Tensegrity part took from us a quite amount of time to decide what is the optimum, configuration at the end of the day we can use that it can fit our application. And to evaluate the Tensegrity statics and dynamics, basically we use these two governing equations that we can that we use to evaluate the Tensegrity structure, Tensegrity robustness against different types of load. So as you know, while drilling, we are going to encounter different types of load, starting from compressive loads, tensile loads, torsional loads, etc. And the chart that you can see here is one of the simulation that we tried to study to make a force analysis about one of the structures that we were developing. So basically what we did, we started to introduce a vibration and try to see the structure reaction and rigidity against vibration. And we introduced, vibration with various amplitudes and frequency. And basically the most common thing we found that the maximum displacement was in the top node in the X direction, and the maximum displacement does not exceed more than 2 millimeters in all simulations. So this tells us like that the structure, the final structure we developed is very robust. One thing I would like to highlight here is if you are interested more in math, and in the stress analysis that we did in the structure, we published a very interesting journal paper 4 months ago about this invention in the International Journal of Solid and Structure. So please feel free to go there and read the article in more details. One important message I would like to highlight here is that when we were establishing and constructing the Tensegrity Drilling Rig, our objective was not only to build a lightweight drilling rig, but we also tried to make the rig deployable. So we are trying, the rig can be put in pieces and move from one place to another place in a very fast way. And here in this video, in animation, I'm going to show you how the rig, how before drilling, the rig can be deployed up. So you can see how the structure, can be deployed up before drilling operation. And here we are going to see how, when we finish drilling, how the structure can be completely deployed down, put into pieces, and move very fast. So the key message that I'm trying to convey here is that we are trying to develop a lightweight drilling structure, but also can be deployed. After we finish our simulation and decided what is the optimum configuration of the Tensegrity network, we started to go to the experimental phase. And basically, the most important part was the Tensegrity structure itself. And here you can see, the schematic of the Tensegrity structure. It consists of different types of components. For example, here you can see the class 1 joint, and the main advantage of this joint is to connect the string from the bottom and top ring. The bottom and top rings actually are used to support the Tensegrity structure itself, and it has hole inside so that the stability rod goes through it, and also the Acme rod. And I'm going to show in a minute what is the benefit of an Acme rod. Also, we had a class 2 joints, and basically the class 2 joints are used to connect the compression members in the structures, that at the end of the day it is bolted with the C joint so that we can connect the strings as well. So each of these component has an advantage and a rule, so that at the end of the day we had a stable Tensegrity structure. Regarding the other component of the drilling rig, it was very close to what we are using in oil and gas. So, for example, we use drilling strings. We also use downhole PHA, where we put our IMU sensors, to measure, inclinations, angular speed, exerted force, etc. And we use drill bit as well. And here you can see a couple of experiments we conducted after we built the Tensegrity structure. One interesting thing I would like here to mention, that basically while drilling, you need to make two types of motion. So you need to move reciprocating up and down, and you need to make a rotational motion. And basically, we tried here to introduce the concept of using a stepper motor and Acme rod. And the basic advantage of the stepper motor and Acme rod is to move the drill string up and down without the need to use a specific, drilling motor at the top. And we go to this solution because we were trying again to reduce the weight, because this is one of the objectives, is to develop a lightweight drilling rig. This was the final shape of the Tensegrity structure, and I'm going to show you a video in a minute how the drilling operation and Tensegrity structure looks like. However, two unique things about this structure I would like to mention. First, you can see how the structure is very light, and this is very important. The second thing is that this structure can be put literally in pieces. And I'm going to tell you the advantage of this in a minute. So the drilling automation team at Texas A&M University, when they started, participating in the speed robotics competition, basically they build a drilling rig, which you feel like it is matching, the current designs that the oil and gas industry were using. And basically, when this rig was tested, it was able to hold 1.5 times of its weight. However, compared to Tensegrity structure, the interesting thing is that till the moment, the rig was able to carry 4.5 times its weight. And the simulation results shows to us it can even carry up to 35 times. That's something we are going to test in the future. Another funny story about this structure, when our teams go to NASA facility in 2021 in Virginia, basically some of the teams complain about, how it took from them a long time, to move their drilling rigs, from one place to another. And of course, because moving a complete rigid structure become a challenge. However, our teams literally put the particles on their backs. And when they go to NASA facility, just attaches the particles and string together. So again, the main benefits about Tensegrity structure, you are speaking about lightweight drilling rigs, but also deployable. So here, I'm going to show you a minute video about, the drilling rig while doing a drilling operation, etc. Basically, here you can see the Tensegrity rig in Texas A&M Drilling Automation Lab with the different components, class 2 joint, ring joints, the swivels, different types. Here you can see the Acme rods that we use to raise and lower the drill string as well. You can see here's the strings, the compression bars. Just like while an actual drilling operation, we were trying to drill a Siemens, and what really you can observe that the structure is rigid. It is not shaking. It was stable and reliable, and we were able to drill through the cement plug. That is something interesting to mention. Okay, so just to save time, I'm going to stop the video here, but please feel free, if you are interested more, to go to YouTube. We already upload the video on YouTube, so you can get more information. So in summary, what I was trying to present today is how we can use Tensegrity concept, to develop a lightweight deployable drilling rig. And this is very important, because if we are able to develop and build a lightweight drilling rig, it is going to facilitate the rig mobility and improving, the drilling performance. Therefore, we are going to minimize the drilling cost. And especially because nowadays, we are speaking about, drilling deep wells, or even in geothermal energy, we're speaking about, using EGS or deep closed loop geothermal systems. And drilling these types of wells, more than 50% of the cost is going to get consumed on drilling. So developing a lightweight drilling rig is going even to help, optimizing the drilling performance in geothermal wells. Also, it is a good way if we are thinking about to send the drilling rig to space, to Mars, to extract water, etc., because you can put the drilling rig literally into pieces. At the end of my presentation, I would like to thank our sponsor. I would like to thank NASA, for their grant to design and build the Tensegrity Drilling Rig. Also would like to thank the Energy Institute at Texas A&M University. And special thanks to Joel Muldenido in Petroleum Engineering Department, the facility manager, who helped us a lot, while building the Tensegrity Rig. Also, we would like to thank Texas A&M Workshop FEDC for fabrication. This part, it took from them a lot of time and effort. Also, special thanks to Dr. Shwama from Zhejiang University of Technology. Here is a publication of the project that we had done. Basically, we submitted 2 technical reports to NASA in 2020, 2021, and both of these reports are uploaded on the internet. Also, here you can find the journal articles that we published 4 months ago in the International Journal of Solid and Structures. And if you don't like to read, directly go to the YouTube video. We mention a lot of interesting stuff about the structure, and even other, other techniques we also applied. For example, water systems, how we are going to extract water from Mars, etc. So at the end of my presentation, I hope you like it, and thanks for your attention. Please feel free to ask any question or have any kind of feedback. Please feel free to reach out through the emails on the presentation. And I guess my colleagues and I will be happy to answer any of your questions. Thank you.
Absolutely amazing presentation. That was, that was some really cool stuff. I'm very curious to be able to hear what the, I know we've got a lot of people that are in the drilling community, right, that are watching this. I'm very curious to be able to hear what some of them and their questions and things that they've got to be able to say. Is there anything else from everybody that's there on the team, anything that you guys would like to add? No? All right, cool. All right, then we'll jump into some of the questions here. I do want to be able to put, King says, interesting compact rig design. I don't know why it's not showing, but Miguel Barrera says that he is sharing this. I don't know why the comment's not showing up here. We do have, all right, some people are starting to comment. We do have this question that comes in from John Dahl. How does it match up with variable loads seen in the drilling process when a BHA gets stuck? Current designs rock the derrick while exerting forces needed to try and free up the stuck assembly. So any thoughts on that? Thanks, John, for the question.
Yeah, I can respond. So basically, when we speak about drilling rig, we speak about, the rig capability, right? So when we had a stuck, we need a hoisting system that you can apply, an overpull or a slack to free your stuck. So basically, till the moment, we did not test the rig, for, freeing a stuck. We only test the rig for drilling. But basically, I guess it will not be a big challenge because at the end of the day, the rig, as I mentioned at the end of my presentation, was able to hold till the moment 4.5 times of its weight and was able to, and based on simulation, it can hold 35 times. So I do believe this is something definitely we can try, but we still think, that the drilling operation was our biggest concern because you are going to face a lot of torsional vibration, etc. So we were trying, first to test the drilling operation, but this is something definitely we can consider. But I just want to stress that the basic benefit of the structure is that it can hold multiple times of its weight so that it can freeze a stuck.
All right. Now we got, I had no idea Robert even watched the show. So now we've got a great question here from Robert Van Kulenberg, who was at last week's IADC Art conference, who asked a lot of great questions. Did you look at getting stands of pipe in and out of the load path? So obviously, this was going to be kind of my question is how are you getting stands in and out? And then how do you do as far as like, is there a racking back function or what is y'all's thought process on that?
Okay, so basically, when we design, if you remember the shape of the Tensegrity rig, it consists of rings, right? One of the things that we think about that we don't need to make a fully circular ring. We can make, for example, 3/4 of the circle or 1.5 of the circle, so that we can make rooms to handle the pipe and put it as a rack back. One thing I would like to highlight is that this is our first trial to build a lightweight drilling rig. And the main reasons that we use this kind of circular rings in the structure, because it's going to support us while drilling and has this kind of torsional loads. So to answer your question specifically, basically, we don't need, to build a complete circle ring. We can just make it from, 3 sides and make a complete room for the pipe so that we can handle it.
Excellent. I mean, it's as long as we can still have a V-door on there, right? Okay. Next question from John DeWart. What is the risk of total structure failure if a single cord fails?
All right. Very good question. You can see that on in our structure there are sidebars and a bunch of strings connecting the bars. What we can do is we can increase the number of bars to increase the redundancy of the structure. So that's a simple technology that we can implement. And by introducing more bars, the structure becomes more robust. And so that's my answer. Thank you.
Excellent.
And I just wanted to add that this, so scaling up, we had simulations going at this stage or this small scale. Now scaling this up for the actual size that we all usually see in real rigs. We did perform some static and dynamic analysis, assuming a bigger structure. And we found out that, in terms of actual loads, there was no potential challenges. Now, in terms of torsional loads and withstanding different natural frequencies and perhaps if the BHA were to be stuck, a different structure needs to be in place, and that's what we are currently researching as well. we have not added any operational settings or operational stages on that simulation. It's only based focusing on the structure itself and how to scale it up, how to scale the concept.
Well, I can say this, with a group of people watching, they could probably come up with a whole bunch of different scenarios to put this thing through. So, John, thank you for your question. Guys, seriously, like, I mean, this is probably some of the coolest stuff we've ever shown here on the show. So now is the time to be able to ask questions. Robert, with another one. On another track, can you clad the outside structure to limit the emitted noise? Geothermal drilling will most likely be in more populated areas. Enrique's shaking his head yes. One of you's got to answer it, not me.
So we did not try it. Moha, what do you think? Do you think like is there a kind of way we can limit the noise when we develop the structure? We did not think about it, honestly, you know, in this situation. Basically, we were mainly focused, you know, on the reliability and robustness of the structure. But this is something, I guess, interesting to think about it and consider.
Yeah. So one idea I'm thinking is that we can add, you know, dampers to the ground that connect to the structure, so it will reduce the vibration noise. And I think there are also technologies that reduce the noise from the motors, right? To add dampers or some sort of a cage to cover the motor and reduce the noise. Very good question. Yeah. Thank you.
All right, next one comes in here from Robin McMillian, who's a guest on last week's show. Be sure to vote Robin. Do you need automated pipe handling to avoid the need for a monkey board?
So I do believe that both of ways, either you are going to manually handling by the direct man on the monkey board, you know, to get the stands, or you can use an automated drill pipe to handle. So I guess both ways, you know, can be applied in our structure. You know, we just need, you know, to put a room for the direct man to stand on and take the stand and put it on the pipe rack. So I guess either, you know, automating it or using manually, as we normally saw in oil and gas rig, can be applied.
All right, now Robert has got two questions. Greetings from Buenos Aires, Argentina. Is there any drilling company interested in making these rigs in a massive way? Question number one. Question number two, if we had stuck pipe drilling, could this rig model provide better performance to deal with this problem? Robert, thank you for your question. I'll let you guys take it away.
So basically, we spoke with two oil and gas companies. We proposed to them the idea, but we did not hear back from them. Also, I do believe that I had a conversation with Qasim before, and he told me there is some interest from other oil and gas company in entering in this area without mentioning names. And by the way, they are competing with the oil and gas industry as well. So, yeah. So to answer the question, yes, we had a couple of conversations, but we did not hear back from the guys. Regarding, I guess, the hoisting system, if we had a stack pipe, could this rig model provide better performance to deal with the problem? So I'm not going to say it's going to provide a better performance or not, because, you know, at the end of the day, any structure you are going to develop, it's going to based on the anticipated load you are going to encounter while drilling. So the purpose of this drilling rig is, you know, is not to, you know, to help in the stuck pipe or to help, you know, in other drilling problems. But the basic advantage of this drilling rig is to build a lightweight drilling rig that can be deployed and move fast from one place to another. So regarding, the stack pipe, as Moha was mentioning, by adjusting, the bars, the strength tension, we can adjust the rig rigidity against different load. And by this way, we can, be able to freeze a stack.
Well, I'm going to add something in there. Based off of the audience members watching this right now, I don't think you're going to have a hard time getting people to call you back. So, but if you do need help with that, feel free to. I can help with the marketing effort there. All right, another question here from John Dell. What time or financial metric determined that quantified the efficiency of rig down / move and up operation that the design would provide benefit for? So essentially, how did you guys measure the fact that you guys were going to be able to rig up, rig down faster?
So, Moha,
and
can
you
share?
You were muted, buddy.
Okay. So I must be new here. I must be new with the online Zoom meetings. No, we did not account for any. That's a great point, and we didn't have any financial or time-wise metric on the scale-up simulations that we had. Again, no operational settings was considered there, but it's just something we need to be doing.
We can get you some numbers. I'm sure of that. All right, Robert. I mean, seriously, like the guys that are asking questions right now is a good group of individuals. Back to traditional derricks. Can a traditional land derrick easily be upgraded to accommodate higher hook loads with this technology? Geothermal needs larger hook loads, but building new rigs could be a financial challenge. Could this be a good solution for this problem? Excellent question. Can we retrofit this?
Okay, so the basic thing about Tensegrity is about the derrick itself. So you can, keep all your technologies the same, your tube drive, your draw works, your mud bump, whatever you want, you can keep it. But what we are going only to change is the derrick, the mast that is above the rotary table. We just want to remove it and put this kind of Tensegrity structure. One thing I would like to add, David, regarding the previous question is, yes, we did not make this kind of financial metrics, but, when you check how much we spend on building this rig compared to the previous teams, how much they had spent to build this rig, there was, I guess, tremendous reduction in expense, because it is just a string, some bars. If you make a good simulation, a good mathematical model, and you optimize the parts, I guess it will not be so expensive. And regarding the timing, I was asking Moha to share his experience about NASA, because I guess Moha, you guys, when you went to NASA, you guys put the stuff in your bags, right?
Right. So we put the bars and strings in our bag and just grab the bag and to the place that we show our structures, and in about like 1 hour we can rig up, we can put the structure up. And for other teams, like the traditional drilling structures, they took a whole day to get all the things ready. So that's another advantage to deploy the structure very fast. Mm-hmm.
Wow. Just the idea of somebody showing up to the rig with a backpack and then like, there's the drilling rig. Just is a very interesting concept. All right. I don't know if anybody else can read this. I don't know if this is a good question or not. It came in on Facebook. Anybody got anything there?
So it is a little bit funny because this is my mom and she's happy. So forget about it. Forget about it again.
Oh, I'm so happy your mom's watching. That's great.
Because she's from Egypt and I had been 3 years, I did not go to Egypt. So she's so happy to show me. So that's it. Forget about it.
All right. After this. This is a Fedor Locksmith first. Well, I'm very happy your mom's watching. Thank you so much for watching. And you need to call your mom after the show gets done. Hopefully it's not too late there. She's still up. So you need to call and tell your mom thank you. This is what the show's about. This is great. All right. See, this wouldn't happen in the SPE conference, right? All right. Do you see any concerns with having this rig walk or skid? Great question. To drill multiple slots on one location. How does the structure handle a cross force like wind? How do you envision assembling the rig at scale? Obviously, in a backpack. Will the assembly need to be at height with significant crane support? That's very important because I know cranes are not cheap. All right. I'll let you guys handle that one while I giggle more.
So, Rupert, do you mind if we allow sharing again?
I mean, yeah, you guys.
Okay. Oh, I have, yeah.
Oh, is yours already up? You wanted me to put it up there again?
Yes.
Okay.
So basically, regarding moving the drilling rig from one place to another, it's very similar to the conventional drilling rigs. Like you have the skids and you move the drilling rig table from one place to another. And what I'm showing you here in this picture was the drilling rig at NASA facility, where we put 2 rails so that we can move in the side and in vertical. So basically the entire structure will be on a table, and by using the skids you can move at any place you want. So I don't see any problem for moving a rig from one place to another. Regarding how does the structure handle a cross force like wind, I do believe we did not study. Moha, can you provide us more insight about it?
We didn't do a wind force study, but what I can think of is when we deploy the structure, we fix the strings and connect it to the ground. And so if the wind is not that too strong, or even if it is strong, we can increase the tension of the structure and without changing the shape to increase the stiffness. So that's one way to solve the problem. Mm-hmm.
Okay, awesome. Regarding like your last question is how do you envision assembling the rigs at scale? So basically, in the journal papers that I referred to was we give an example about a drilling rig which was 142 feet. It's a conventional mast we use in oil and gas industry, and the maximum load was expected from this conventional drilling rig was around 750 kilopounds hoisting loads. So when we run our simulation for the scale up, what we really find that the Tensegrity rig, you will only need around 14.3 tons of the Tensegrity. So imagine you have a rig, weight only 14.3 tons, which is something compared to the conventional drilling rig is a massive reduction in weight. And we are going to build the structure basically by using the bars will be from steel and the OD will be 6.625. So please, Andrea, if you are interested more about the scale up, I guess we make a dedicated section in the paper about this part. And I really hope that this answers your question.
Well, the other part of the question was, will the assembly need to be at height with a significant crane support? Would you need crane support to be able to get this stood up? So I guess we might need a crane, at least for the top ring, right, to install the top ring of the structure. Yeah, I do believe we still need a crane, and crane is almost in any drilling oil and gas well, you will find a crane standby. So yes, I definitely to move the crane to move the rings from bottom to top. Definitely, we will need a crane. All right. Another question. Any plan about further optimization of the structures to increase the load/weight ratio, like shape, size, numbers of sidebars, or 3D shapes of the main support structures? Or what's the inspiration of the design? Any mutation?
All right.
This sounds like somebody with a PhD.
Yes. All right. Very good question. For further optimization of the structure, what we can do is from the mechanics and materials, when we change the single bar, so currently we are using the circular bars. But if we change it to a triangular shape of the bars, we can save 17% of mass than this structure. But manufacturing the triangular bars would be more complicated. And for the shapes, for the shape of the sidebars and the 3D shape of the main support structures, we need to specify. So for example, if we want to increase the redundancy of the structure, and so for example, we do the failure study, one bar fails, and we increase the number of bars. That's a trade-off, because when we increase the number of bars, we pay more mass. And the inspiration of the design is so for a single bar, we give a compressive load. The bar is easily to buckle. But if we put the same force to a shorter bar, the bar is harder to buckle. The problem is when we cut the single bar to 2 bars, there will be a global buckle. So for example, the bar will global buckle. And what we do is we add a string to the joint and stabilize the structure. So we reduce the mass by cutting the long bars into short bars and add strings to prevent the global buckling of the structure. So that's the idea of the compressive efficient structure that we use in this design. Thank you.
Excellent. Well, for everybody out there that's still watching, like I mean, normally this might be the time that I cut the show, but I've still got questions, and I think that there's a lot of really good information that we can still glean for this. So I got a couple of things that I want to throw out there, and you guys can just jump in and talk about them. What about? I know you guys didn't specifically look at operations and stuff, but what about coil tubing or using something like this as a workover rig structure? And then also about what about tripping, right? Because I know that I've had Dr. Teodoro from OU on, and he says the majority of the time rigs are not actually drilling, they're tripping, so they shouldn't be called drilling rigs, they should be called tripping rigs, right? So what is y'all's thought process on like I said, coil tubing, tripping? I can't even remember the other thing I said, but you guys jump in there and give us your thoughts.
So hello. So I'm going to jump on that real quick. Regarding coil tubing, we've actually done some upgraded design over last year with our new team, and our concept was to use the concept behind coil tubing drilling in order to allow us to continuously drilling without having the issue of having to trip back out constantly. The main reason why was because the plan was to be able to drill up on the surface of Mars, and once we reach the ice, we should be able to kind of melt it and then produce water from it. And therefore, in order to make that process more efficient, and since it was going to be done kind of remotely, we had planned to have a coil tubing drilling system in order to accommodate for that. So that's definitely possible. And once again, this concept can be applied to many different fields. The only limit that you may have is going to be your imagination, right? I was thinking about having a few pictures of what different teams did, but I figured that we're not here to pick fight with anybody, so I'm not going to take shots at anything. But the reality is that our concept really, what was very nice about it is that we showed that by using strings in tension and bars in compression, we could make a lightweight structure that can be easily assembled and disassembled in order to be able to drill any kind of well, pretty much. Dr. Khaled showed us a picture of the previous rig design, which was very heavy, very hard to move, and I can attest to that. We had to move it up and down our building, and that was not an easy thing to do. However, for our lightweight concept, I kid you not. I literally just took my suitcase from my bedroom. I brought it to the lab, took the rig apart, put it in the rig, and then just flew with it as if I had normal normal language. So therefore, this concept is very applicable to any field. And regarding the issue behind tripping in and out, the concept can also be upgraded, right? So the picture we showed was to kind of how to drill in one sequence. However, we don't have to just rely on that one picture, right? Like Dr. Moha mentioned, with the string in tension and the bars in compression, we can redesign and upgrade any kind of system. It's just going to be a matter of having the right amount of data set in order to run the different simulation. I've seen some people mention questions about the geothermal field, and I can tell you on the geothermal field, I've been actually working on a geothermal drilling project up in Utah, and we have a whole lot of vibration, a whole lot of noise, like he said. And I remember that one time I was in the company. I was with the company man in his shack, and I could see the rig vibrating so much that I was afraid that one pipe was just going to shoot up and then come hit me right in the face, right? So that is a reality. However, our design can, with the right amount of data set and the right amount of simulation, can withstand those type of process. It's just a matter of having a good idea of what we want to do, and then just redesign the different structures around it, so that we can pretty much change the structure with different strings and bar in order to allow us to kind of transport it a bit easier. And this kind of concept is in my opinion very useful for application in very remote areas, right? Such as Alaska, in places where we want to have testing, or maybe for our men and women out in the field who needs to drill real quick for some water, right? If we have a system that can be easily deployable and easily carried, like anybody can kind of use it in any field in order to be able to achieve what they need to achieve. So I guess my answer is yes, it is possible. It's just having a clear sight of what you want to do, and then the only limit is going to be your imagination, pretty much.
Excellent, thank you, Dr. Eduardo. You wanted to jump in on any of this? Mute.
Yeah, I was mute. Yes, no. I think no, everything that what was discussed was a really good points. I just want to stress that this was our first attempt to do that, right? And you guys bring up a lot of good questions to be solved, which makes us happy that we have some more work to do, right? But let me just jump in then and say that Texas A&M, we are working with Texas A&M on a patent on that. So if there's anybody interested on learning some more, just feel free to contact me, or I can put you in contact with our person that is dealing with the patent. There's and I must stress as well that this was something that was developed entirely from with students, right? We as a faculty had a very little voice, if you can say that, right? But they are all magically developed this idea. So that was a very good undertaking.
Excellent. Well, guys, thank you all so much for being here. Any last words, anything else that you guys want to be able to share? I don't have any more questions for you right now. I've asked kind of mine. A lot of the stuff was already kind of covered while we were going through. Anything from you guys? Enrique?
Yes, I would like to add that this has been really helpful. Just getting the insights from people that are already in the industry has given us some more, even outsider of the box or outside the box thinking in terms of what we wanted to do next. You brought up, David, the perfect point of the workover rigs and the tripping and cold tubing that we had not considered, or the retrofitting the geothermal drilling rigs. That I believe those are huge and valuable insights that we honestly, it would have taken us way longer to think about that, because we focus mostly on the analysis and the dynamics and on the academic side of things. This has been really helpful for us as well. Thank you very much for inviting everybody and inviting us, and thanks for your time, guys.
All right. Well, guys, thank you guys so much for being here. For everybody watching, I do appreciate it. Next week, we've got James Mann coming on, and he is going to be talking to us about supply chain in the oil and gas industry. Week after that, I don't actually think I have a guest lined up yet, so I need to get busy doing that. If you guys haven't already, like, share, subscribe, do all the social media things that help us out. We do appreciate it. Try to see. Okay, there's some questions that are coming in, just a little bit of banter there in the background. But for everybody out there, thank you guys so much. You guys stick around. Don't jump off just yet. But everybody out there, thank you guys so much for watching. Really do appreciate it. And as always, know your industry.